AP Calculus BC, Unit 7, Day 10, office hours. A little bit of free response review, nothing too big. Should take about 15 minutes or less. I'd say these usually probably take 10. Okay, so this is graphing calculator problem. The R be the region bounded by the graphs sine pi x, which that's what this one looks like. I'm going to label my picture a little bit more. The period would typically be 2 pi, but then you divide by the coefficient inside from the x, and it gives you period 2, which makes sense. Then this is a cubic. This is the cubic, 4x cubed minus 4 y equals x cubed minus 4x. Okay, find the area. I think we're going to probably want to go with a vertical slice. Horizontal slice would involve inverse sine, which we don't know how to integrate, so I don't think we should do that. There is a creative way you could do this problem too. That would make it a little easier. So the region R, the area of region R, is going to be the integral left to right, 0 to 2, y top, which is the sine curve, sine pi x, minus y bottom, which is the cubic, put it in parentheses, x cubed minus 4x, close parentheses, dx. So that's your setup, which is good enough. Then you use your calculator. And we're going to do math 9 sine pi x minus x to the third. I'm going to distribute the subtraction plus 4x, comma x, comma 0, comma 2. And the answer is nicely 4. I'm going to just write 4.000 because I did my calculator, and I want to just communicate that I was aiming for 3 decimal point accuracy, and I didn't round to the nearest whole number for some reason. 3, 2, 2, 2. Now, by the way, a creative approach is you could have put this guy into this hole, and then it would have just been a different approach. It would have been 0 to 2 of negative x cubed minus 4x dx. This should give us the same answer. Not that you would need to do it that way, but let's just check it out. Math 9, negative x to the third plus 4x, comma x, comma 0, comma 2. Same answer. Pretty cool, huh? All right. Horizontal slicing would be a nightmare, and I just don't think we do it. We can't. We involve an inverse sine. There's no way we can solve this x in terms of y by hand, so that's just not even an option. Okay, B says a horizontal line y equals negative 2. Y equals negative 2, which would be right here. Y equals negative 2 splits the region into 2 parts. Write, but do not evaluate integral expression for the area of the part of R that is below this line. So we are going to have to, I think we're going to have to kind of do like horizontal slicing here. No, we can do vertical slicing. So this would be y top and this would be y bottom. Horizontal slicing is still not going to work. You're not going to be able to solve this for x in terms of y, which is what you would have to do for horizontal slicing. The one thing we do need to figure out are these intersections. So I think it's time to go ahead and graph these. So x to the third minus 4x. And I'm also going to graph negative 2. The window is going to be 0 to 2, I guess, is good. And then in the y, negative 3 to 1. So this is just graphing the cubic. So there we go. We got to find these intersections, second calc. Intersect, first curve, second curve. I'm going to guess like 0.5 for the first one. And it is 0.5391887 comma negative 2. Second calc. Intersect, first curve, second curve. 1.7 is my guess. 1.6751309. We need to write more than 3 decimal places. Several more in the middle of our work. So those are the limits. I mean, I guess we could have done it algebraically or showed work, for how to do that. But so the area is going to be 0.539188887 to 1.6751309. Y top is -2. Y bottom is the cubic. X cubed minus 4x. Make sure you distribute that subtraction or just put parentheses. And then we're going to calculate it on our calculator. So we're going to do math 9. We're going to do -2 minus x to the third plus 4x, comma, x, comma, 0.539188887, comma, 1.6751309. And that's, it said not to solve it. Okay. All right. So I guess that's it. I mean, we were able to. 0.811425, but they told us not to. That's fine. So that looks good. Point-wise is 1 point for the limits, 1 point for the integran. On the first part, it was 1 point for the limits, 1 point for the integran, 1 point for the answer. Okay, so now we're going to part C. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. So I'm just going to use my little vertical slice I drew for part A and draw a square for it. Kind of emphasize the three-dimensional kind of part of it. So that's one slice. This is volume by cross-section. So every slice should be some common area formula in terms of x. They will be squares, which will be side squared. So I kind of like to just run through those motions real quick. Now the limits are going to be in the x direction. So it's going to be 0 to 2. The sides are y top minus y bottom. Y top is the sine curve in terms of x, and the cubic on the bottom in terms of x. So parentheses sine pi x minus parentheses x cubed minus 4x, close, squared. Don't forget the extra squared. And that's your answer. That's your setup. And now we can calculate it on our calculator. I feel like, yeah, that's fine. Okay, so let's see, math 9, parentheses, sine pi x, close parentheses on sine, minus x to the third plus 4x, close parentheses, squared, comma x, comma 0, comma 2, and see what we get. 9.978, 3 decimal accuracy, rounded truncated, comes out the same this time. All right, D, the region R models the surface of a small pond. At all points R at a distance x from the y-axis, the depth of the water is given by h equals 3 minus x. Find the volume of the water in the pond. So this is kind of interesting. If you think of this as the top of a pond, and then it goes straight down on the sides, I guess, and so the slices below it are rectangles. But the height right here is changing based off of this curve. So they're not, it's kind of like volume by a cross section with rectangles below. And so it's, some common area formula in terms of x, which is going to be a rectangle, which is going to be base times height. So for us, the limits are 0 to 2. The base of the rectangle, I would consider that is this same y top minus y bottom. It's sine pi x minus parentheses x cubed minus 4x. So that's the base. The height is 3 minus x. They gave that to us, right? dx. So that's your setup. And now we're going to plug it into our calculator. Can I make use of my last calculation? I think so. I just need to get rid of the squared and put parentheses, second insert 3 minus x. So just taking advantage of what I typed in before. And we get 8.369 or 8.370 if you want to round. Points on that, 2 points. That's it. 1 point for the setup here and 1 point for the answer. On the last part, part C, it was 1 point for the for the setup and 1 point for the answer. So the part D was a little weird. All the other parts were pretty kind of straightforward-ish type of area volume problems. Okay, and we did it in 11 minutes. Okay, let's try another one. The storm washed away sand from a beach, causing the edge of the water to get closer and closer to a nearby road. The rate at which the distance between the road and the edge of the water was changing during the storm modified FT. So that's the rate of change of the distance between the road and the edge of the water. T hours after the storm began. The edge of the water is 35 meters from the road when the storm began. So that'd be like the distance, we call it distance at time 0 was 35. The storm lasted 5 hours. So those are going to be endpoints. So T is 0 to 5. So we got a bunch of good information. And then they gave you the derivative. So they gave you the function, and then they gave you the derivative of it. We could have found that derivative ourselves, so whatever. That's nice, though. They gave it to us. A says, what was the distance between the road and the edge of the water at the end of the storm? Well, that would, let's see. The rate, no, this is the rate, and this is the rate of the rate. Okay, so this is the rate. So if we know, it says, what is the distance between the road at the end of the storm? So we want to know D5. We know D0 is 35. And we know D prime equals FT square root of T plus cosine T minus 3. So I'm just kind of summarizing the important information we use. So I think it's the fundamental theorem of calculus part 1. If I integrate D prime, I get D. And if I go from 0 to 5 and plug limits in, smallest biggest, top first, bottom second, subtract. So I want D5. So D5 equals D0 plus the integral 0 to 5. Now D prime was f of t. So then D5 equals 35 plus 0 to 5 of square root of t plus cosine t minus 3 dt. Now, I have a feeling that we might be integrating this or doing stuff to it multiple times. So I'm going to go ahead and enter my calculator. I don't know, just because it might save me time. If not, I think I'll be all right. Like, it's not going to cost me much extra time because I'm going to use it right away right now. Just make sure I entered it in correctly. One benefit of that is saving time. It's also making sure you do it right the one time, and then you don't have to mess it up before. So we're going to do 35 plus math 9, vars, y vars function y1, comma x, comma 0, comma 5. Oh, didn't like that. Square root of x plus cosine x minus 3. Oh, I put it in the wrong spot. That's fine, whatever. I put it into y2 accidentally. Okay, so I can just copy and paste this and go back up here and do vars, y vars function y2. I just got to remember, I guess I put it there now in the future. And the answer is, waiting, 26.494, or, and the units are meters, might be good, or 26.495. Point breakdown on this problem, I actually don't have it written down, so whatever. Okay, B. Using correct units, interpret the value of f prime of 4 equals 1.007 in terms of the distance between the road and the edge of the water. Units. So you're not even calculating anything. They gave you this. I guess we could have calculated it, but they're saying interpret it. Now, this is the derivative of the derivative. So this is the rate of change of the rate of change. So we could say something, we need to describe the time 4 hours after the storm began. The rate of change. So one thing that usually going to go for on derivative, if it's positive, you're going to say something is increasing. You're going to say f is increasing. If it's negative, you're going to say f is decreasing. Now, f is the rate of change. So I'm going to say the rate of change is increasing. The rate of change of the distance between the road and the edge of the water is increasing at a rate of 1.007 meters per second or meters per second squared. Got to put the units in here. That's part of it. So I know it's meters per second because f was meters per second, and this is the derivative of f, so it's per time again. So it's another per second, kind of like acceleration. Okay, C. At what time during the 5 hours of storm was the distance between the road and the edge of the water decreasing most rapidly? Decreasing most rapidly. Now, this sounds like extreme value theorem to me. This sounds like a absolute max or absolute min. I'm thinking decreasing means it's the most negative. So we're looking for the min. And we want to do EVT. Now, the endpoints they gave us, they said during the 5 hours of storm. So the endpoints are 0 to 5. And decreasing most rapidly. So that's the min f. So we need to take the derivative of f, which they gave us, and or we could do it again ourselves, equals 0 undefined. And for sure, undefined is going to happen when t equals 0. And then on our calculator, we could solve the other part. So I'm going to turn this guy off, and I'm going to graph this equation and find its x-intercepts. That'll give us divided by parentheses 2 square root x, close, minus sine x. I'm going to go to the window. I'm only concerned about 0 to 5, and I'm just looking for x-intercepts, negative 1 to 1 on the y. We'll just focus on the x-axis. There's one. Might be more than one. There's another one. And so we need those two right there. Second, calculate 0. Between 0 and 1, I'm going to guess 0.7. There it is. So we're going to write t equals 0.661865548. Carry more decimal places. You're going to use these in calculations. Second, calculate 0. Looks like there's one around 3. So I'm going to say 2 to 4, guess 3. Okay. 2.843832. So these are the critical points. And now we're going to make a table. So time, and we're going to plug these into f, the original function that we're trying to find the minimum of, the most negative. We have 0, 0.661865548, 2.843832, and 5. Now I do have this equation entered into my calculator, I think. Yeah. And get rid of that. So that's that equation. So I can go to the table, and I'm just going to get rid of what's there, and then we type in 0, and then point. Oh, I also need to go turn this back on. I turned it off. 0. It wasn't showing up here, which means it wasn't on. 0.66186548, 2.8403832, and 5. And I'm going to go over here and highlight these because they're going to be rounded to decimal places I don't want to round to, just to make sure I write the right thing. So this is negative 2.00. Next one is negative 1.397601. Next one is negative 2.269634. Next one is negative 0.480269. So which one is the min? Right there. That's when it's decreasing most rapidly. So we're going to say the distance says distance between the road and the edge of the water is decreasing most rapidly at a rate of negative 2.269. You could do negative 2.270. What are the units? Meters per second. At time t equals 2.840 hours after the storm began. That's a very thorough answer. Okay, now what's your justification? By extreme value theorem, checking endpoints and critical points. That's an answer. All right, last part D. D says, after a storm, a machine pumped sand back onto the beach so that the distance between the road and the edge of the water was growing at a rate of GP meters per day, where P is the number of days since pumping began, but it started after the storm. So it almost sounds like a rate model, like where you have an entering rate and leaving rate, but this is just going to have the entering rate after everything got left. Write an equation involving an integral expression whose solution would give the number of days that sand must be pumped to restore the original distance between the road and the edge of water. So you want to get back to the original amount. Essentially you want the sand, the distance that was taken away, be added back, right? So it is kind of like a rate model, and you want it to equal out. So we could say, well, the sand that was taken away was this original function, right? That was the rate. And then, it turns out this is, yeah. And then we're going to subtract, or no, then we're going to add, because this turns out to be negative. Then we're going to add the sand coming back, 5 to some time t of the rate coming back. Now, so it says, P, we're supposed to use P as the input variable here. Okay. So I think, and we'd want that to equal 0. We want that to equal each other out. Meters per hour. You can see that F is negative, right? So when we integrate F, we're going to get negative you get a negative number here for the sand that was lost. This is going to add the sand. So, I mean, another way you could do it is you could say, oh, wait. Let's see. I think we'd say 0 for this guy because this function starts at time 0. Time 0 is after the storm began. So P is the number of days since the storm ended. So that should be a 0. This 0 is different, but this function, 0 means something different to this function than 0 means to this function. So kind of tricky. But that's it.